In this video, we're going to learn how to graph exponential functions with transformations. So I rewrote a lot of the transformations we've gone over in the past, but in the exponential form. So first, starting with the number that's in front of b to the x, the a value will correspond to a vertical stretch or a compression, depending on if the value is greater than 1 or between 0 and 1. And I'm looking at the absolute value of it because I'll go over what happens with the negatives later. Translations will typically be if it's subtracted from the x in the power, that corresponds to a horizontal translation, while adding or subtracting a value will correspond to a vertical translation. So that's where your shift will be. And if there's a negative in front of the function, that corresponds to a reflection across the x-axis, while a negative right by the x actually corresponds to a horizontal reflection across the y-axis. Now altogether, that looks like y is equal to a b to the x minus h plus k. Or if it had any of those reflections, you have a negative a value in front of the b, and then to the negative x minus h. And very key here, it looks like that negative is factored out of that expression. And we're going to see how that comes into play later in an example. But first, let's graph this function. And before I graph, I want to actually point out all the transformations taking place. So what I see here is I do have a negative out in front. So this will be a reflection in the x-axis. So meaning that my final product of my graph will end up below the x-axis. And then the 1/3 in front of the 3 to the x actually corresponds to a compression, because 1/3 is between 0 and 1. Again, you're seeing me ignore the negative that's in front of the 1/3. So this is a vertical compression by a factor of 3. And then after I graph, I'm going to go over domain, range, and whatever in the horizontal asymptote. But after I graph, so you can see how these things have changed from their usual positions, if they've changed. So I'm going to use a pencil. I'm actually going to start by just graphing 3 to the x, so you can see what happens with the transformation. So 3 to the x, if we plug it in 0 for x, you'll get 1. I'm going to use a pencil because it's not the final answer. And I plug in 1, I get 3. 3 to the first is 1. And then 3 to the second is 9. And then 3 to the negative 1 is 1/3. And then negative, and then 1/9 for 3 to the negative 2. So we'll see here that we get this exponential function. But when I apply the transformations, ideally just multiplying each point by negative 1/3. Let's see what happens. If I take 9 and I multiply by negative 1/3 to get that change in the y value, because it's by a factor of 1/3, not 3. I will multiply 9 by 1/3, so it brings it from 9 to 3, and then it reflects across the x-axis. So you could also just multiply 9 by negative 1/3, and that puts it down here. If I take this 3 point, multiply by negative 1/3, it puts it at negative 1. Multiply 1 by negative 1/3, puts it at negative 1/3, and then it starts to flatten out along the x-axis again. So we end up with this graph after applying the transformations. So I still have that asymptote at the x-axis. So it still flattens out there, so my horizontal asymptote will still be y equals 0. And I'm going to erase away my other graph because I don't need it anymore. It was just to show that transformation. But now I'm going to see my domain is still all real values of x. So that still goes from negative infinity to positive infinity. or all real numbers. And the range now, instead of going from 0 to infinity like we've seen it happen before, it's actually going from negative infinity to 0. Or y is less than 0. It's everything below the x-axis. Let's try another example, but you see now how it transformed. Now I'm pointing downward. Just to let you know, since that a value here is negative and this is now falling rapidly, this is not exponential growth or decay because the a value is negative, so we can't call it that. So up here, let's look at y is equal to 2 to the negative x plus 4. Now before we start, I mentioned this. We have a negative by the x, which corresponds to a reflection, but in order to see what the horizontal translation is going to be, we actually need to factor out that negative. So we'll have 2 to the negative of x minus 4. So instead of it being plus 4, which would correspond to a translation to the left, it's now minus 4 because I factored out that negative, which actually means it's a translation to the right. But now let's go over how to graph this. And it's going to start with a parent function that's very simple. It's like y is equal to 2 to the x. We'll see how it changes from this. And what I can already tell is that there is that negative out in front means there is a reflection. In the y-axis this time, which I'll go over in a minute. And I see a horizontal translation right 4. But let's start off by just graphing y is equal to 2 to the x. So if you plug in 0 for x, that's 1, because 2 to the 0. 2 to the first is 2. 2 to the second is 4. And 2 to the third is 8. That goes all the way to the top. And then if I plug in negative 1, that's 1/2. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4, and so on. And we'll see it kind of flatten out here. Next up, I'm going to take care of this reflection and the y-axis, which means every point reflects across the y-axis. So this point reflects across from 2, 4 to negative 2, 4. This point goes from 1, 2 to negative 1, 2. The y-intercept stays the same. And then the point at negative 1, 1/2 goes to 1, 1/2. And the point from negative 2, 1/4 goes to 2, 1/4. So the difference is now it flattens out against the x-axis, but instead of being exponential growth, it actually is going to be exponential decay. And I'm going to erase that other graph so it doesn't get in the way for my final problem, because I don't need it anymore because now I've reflected it. And now we're going to shift everything to the right 4. This will be our final graph because it's the final transformation. So every point goes right 4. So this one goes 1, 2, 3, 4 to the right. The one at 8 also goes 1, 2, 3, 4 to the right. Then 1, 2, 3, 4 to the right. 1, 2, 3, 4 to the right. 1, 2, 3, 4 to the right. And 1, 2, 3, 4 to the right. And now it goes still exponential decay, but now you can definitely see it shifted to the right 4 units. With that horizontal asymptote actually continuing to be at y equals 0 as well. Then I erase away the other graph because I've now transformed it, so I don't need that there anymore. But now if I go through my domain range in a horizontal asymptote, my domain is still all real numbers. You can plug in any value of x that you want to. So negative infinity to positive infinity, or you could write all real numbers with a bold R. The range is still all positive values of y, so from 0 to infinity, or y is greater than 0 this time, and the horizontal asymptote is still at y equals 0, also known as the x-axis. So in this case, even with all the transformations, the domain range and horizontal asymptote still stayed the same for the general parent function of this graph, which is like y is equal to 2 to the x. Now let's look at this last example. As I can already tell here that I'm going to have two transformations taking place. This is a graph of exponential decay, because 1/2 is less than 1. But with that 20 in front, there's a vertical stretch by a factor of 20. And we'll see how that affects the graph in just a moment. And then we add 10, so that's a vertical translation up 10. So now let's see what happens to the graph. Now, one thing that can definitely help is to use a parent function, and we actually went over in a previous lesson how we can graph y is equal to 20 times 1/2 to the x. We'll actually start there because that 20 usually corresponds to a y-intercept, so I know that it crosses the y-axis at 20, and we can find more points where we need them. If we plug in 1, that will just be 20 times 1/2, which will be 10. And if we plug in -1, that'll be 20 times the reciprocal of 1/2, which will be 2. So 20 times 2 is 40. And these functions always flatten out at the x-axis. So if you need 40, that's 30. 40. But if you need more points, just plug in more. So plug in 2, that's 1/2 squared, which is 1/4. 20 times a fourth is 5. That should be enough just to start graphing this function that flattens out at the x-axis, as it typically does. And that already incorporates the vertical stretch, since I used it as a y-intercept to graph this time. Now we just need to incorporate the vertical translation, which originally my asymptote is at the x-axis. So when I shift things up, that asymptote will actually shift up as well to y equals 10 this time. And every point gets shifted up 10 units. And this will be the last thing. So this point goes up 10. So it's 1, 2, because I'm counting by 5s. Up by 10. So 10 goes to 20. 20 goes to 30. And then 40 would go to 50. That's off my grid. But I can now see where this starts to flatten out. So I'll come down and flatten out against the horizontal asymptote, which shifted from 0 to 10 when it went up by 10. And now I'll erase away the original graph so you can focus on where the graph is now. Now you'll see the importance of drawing out that asymptote, because up to this point it's always been the x-axis. But now you can see why we draw it out, because now you can see, oh, it flattens out at a different spot on the graph. So my domain for this problem is still all real numbers, -infinity to +infinity. The range in this case is the lowest it can ever reach is 10, but not quite. So I go from 10 to infinity, or you just say y is some value greater than 10. And the horizontal asymptote actually changed this time to y equals 10, that horizontal line right there. And that is how you graph exponential functions with transformations.